So in this lecture and a lecture tomorrow, I'd like to focus on this hypothesis called ER equals EPR in the context of the question whether it can be interpreted as a duality between topology and entanglement. So that's one aspect of duality that's associated with this hypothesis. Another aspect, as we'll see, is that it's intimately related to the ADS-CFT correspondence, insofar as one of its initial motivations comes from a particular, what we might think of as a particular entry in the ADS-CFT dictionary. So by way of at least initial introduction, right? So this ER equals EPR hypothesis was presented in a paper by Maldaceno and Susskind in 2013. Before I forget, right, please don't hesitate to interrupt me with any questions at any point. So this is supposed to be my attempt to understand the ER equals EPR hypothesis. So I don't promise that it's a rigorous understanding, or even if it's an adequate understanding, but it's my attempt to understand it. Right? So the ER equals EPR hypothesis, simply put, is the claim the subsystems of a composite system in a quantum entangled state, that's the EPR part of the equation, are connected by an Einstein-Rosen wormhole, right, the ER part. So it's extremely simple to state, right, on the surface, but it has potentially profound implications. Right? I mean, is this a way to reconcile an essential aspect of quantum theory, on the one hand, entanglement, with a fairly unique aspect of general relativity, right? The existence of space-time solutions to the Einstein equations that can be interpreted in terms of a wormhole. Can it be interpreted as a duality between entanglement and space-time topology? One of the initial uses that Maldaceno and Susskind put it to in their original paper was they proposed it as a solution to the firewall problem in the context of the black hole information loss paradox. And moreover, in this article, they point to intriguing similarities between quantum entangled states and wormholes. For instance, they observe that both cannot be used to send superluminal signals, and both are not affected by local operations appropriately construed. In this lecture, I'd like to, this lecture consists of essentially a review of kind of the basic aspects of wormhole spacetimes and general relativity, and how spacetime structure might be associated with quantum entanglement, and then a brief discussion of the initial motivation for the ER equals EPR hypothesis. And in the second lecture tomorrow, I'd like to consider additional motivations that have appeared in particularly in the physics literature since Maldaceno and Suskind's article. But this first lecture I've organized into three parts. Right? So the first part is a review of wormhole spacetimes in general relativity. So I'd like to start kind of with a warm-up exercise, reviewing basic aspects of Minkowski SpaceTime, and then move on to two examples of wormhole spacetimes in general relativity, extended Schwarzschild spacetime and extended ADS Schwarzschild spacetime. And then in the second part, I'd like to consider how entanglement might be related to spacetime structure in the particular context of quantizing a field in a background spacetime. So I'll first look at the example of field quantization in Minkowski spacetime, and then it's a fairly simple step to consider field quantization in extended Schwarzschild spacetime. And with those two examples in hand, and the last part of this lecture, I'd like to consider this initial motivation for the ER equals EPR hypothesis that Maldacena and Susskind discuss in the very first part of their paper. And this is an example due to a previous article by Maldacena in 2003, in which he proposes a correspondence between extended ADS Schwarzschild spacetime on the one hand, and a particular entangled state in a conformal field theory on the other hand, what's called the thermofield double state. Right? And this example is presented in the context of the ADS CFT correspondence. All right, and again, I'll leave additional motivations for ER equals EPR to tomorrow's lecture. The first part, let's begin a brief review of basic features ultimately of wormhole spacetimes and general relativity. For this review, I'm relying heavily on Sean Carroll's textbook on general relativity. I believe it's entitled Spacetime and Geometry, as well as a review article by Daniel Harlow from 2016. This is his Jerusalem lectures on black holes. Let's remind ourselves of basic properties of Minkowski spacetime. So Minkowski spacetime is the unique zero curvature vacuum solution to the Einstein equations with spacetime interval expressed in what we might call the Minkowski inertial coordinates, Px, y, z, given by this hopefully familiar expression, right? So really this is a way of calculating distances between points in Minkowski spacetime. It's a way of representing the metric. Right? The distance between a point labeled by coordinates Tx, y, z, and a point that's infinitesimally close to that point labeled by coordinates dt, dx, dy, and dz. So the distance formula, the interval formally looks like the interval for a standard Euclidean space, right? In this case, a four-dimensional Euclidean space, except of course for the minus sign in front of the time coordinate term. And of course, the Minkowski spacetime interval can be expressed in different coordinates, right? So in spherical coordinates, TR and these two angular coordinates, it takes this hopefully familiar form. The transformation between inertial coordinates and spherical coordinates take these forms. Right? Now, Minkowski spacetime can be thought of as an extension of a smaller spacetime, which is referred to as Riddler spacetime. And the reason why I'd like to review this feature of Minkowski spacetime is going to be because, as we'll see, the two examples of wormhole spacetimes that I'd like to consider also have this basic feature. They can also be thought of as extensions of smaller spacetimes. To understand how Minkowski spacetime can be thought of as an extension of a smaller spacetime, Riddler spacetime, we're asked to first consider what's called the right wedge of Minkowski spacetime. That region of Minkowski spacetime described by this relation between the x coordinate and the time coordinate, suppressing the y and z coordinates for convenience. So that corresponds literally to a wedge, right? If Minkowski spacetime is thought of as a two-dimensional surface, then it's this right wedge region of it that corresponds to this constraint on the coordinates. This right wedge is sometimes referred to as the right Riddler wedge of Minkowski spacetime. And we can introduce a new set of coordinates called Riddler coordinates that cover this right wedge of Minkowski spacetime. Eta psi, where eta is the Riddler time coordinate and psi is the corresponds roughly to the radial coordinate, the spatial coordinate. And Riddler coordinates are related to standard inertial coordinates, right, by these hyperbolic trigonometric functions. Now it turns out in this right wedge of Minkowski spacetime, an eta time translation can be shown to be equivalent to a Lorentz boost in inertial coordinates, Tx coordinates. And one way to show this is by taking the generator of translations in the eta direction, eta time direction, which is this vector field, d by d eta, and just applying the Riddler coordinate transformations, the inverse of the Riddler coordinate transformations to it. And what you get is the vector field on the right, which turns out to be the generator of Lorentz boosts. And taking a step back, right, a bit of terminology. Both time translations and Lorentz boosts are symmetries of the Minkowski metric, and a vector that generates a symmetry is referred to as a Killen vector. The Minkowski interval can be expressed in terms of Riddler coordinates, and in Riddler coordinates, it takes this fairly simple form. And then again, Riddler spacetime can be simply defined as the right wedge of Minkowski spacetime. And its interval again in Riddler coordinates is given by this expression, where the Riddler coordinates have these corresponding ranges. So to visualize this idea of viewing Minkowski spacetime as an extension of Riddler spacetime, we can let's consider this diagram on the left. So I've taken this diagram from the review article by Harlow. This is a spacetime diagram of Minkowski spacetime suppressing the y and z coordinates, and it's divided into 4 regions. Right, there's the right wedge region represented by this blue wedge. Then there's a corresponding left wedge, the other blue wedge, and then the other 2 regions are the green and red regions. And again, Riddler spacetime is to be identified with the right blue wedge region. Within Riddler spacetime, the region R, curves of constant Riddler coordinate psi have the following 3 features, properties. They're a hyperbola given in inertial coordinates by x squared minus t squared equals constant, with asymptotes at x equals plus or minus t. These are the 2 dashed lines that form the boundary of the R region. Curves of constant psi are also orthogonal to eta equals constant surfaces in Riddler spacetime. So the eta equals constant surfaces are space-like surfaces, slices entirely through Riddler spacetime. And it turns out they form what are called Cauchy surfaces. Right? So a Cauchy surface is a space-like surface such that any causal curve that's extended indefinitely either in the future direction or the past direction ultimately intersects the surface at a point. The eta equals constant surfaces in Riddler spacetime have that property, and it turns out the collection of all eta equals constant surfaces form a foliation, completely foliate Riddler spacetime. And the last property of curves of constant psi in Riddler spacetime are that they turn out to be the integral curves of the generator of translations in the eta direction, right? This Killen vector. All right. Now, one feature of Minkowski spacetime that you can then prove is that is the claim in this brown box. Namely, it admits what's called a bifurcate Killen horizon. So in particular, the null surface given by x equals plus or minus t, right? That's the 2 dashed lines in this diagram, forms this thing called a bifurcate Killen horizon generated by the generator of eta time translations. So the fine print here is a bifurcate Killen horizon is the union of 2 null hypersurfaces, right? These 2 dashed lines that intersect in a space-like 2-dimensional surface. In this case, this is the origin, the point at the origin of the xt coordinates, and that are both Killen horizons with respect to the same Killen vector, So a Killen horizon is a null hypersurface that's everywhere normal to a Killen vector, right? And the relevant Killen vector here again is this generator of translations in the eta direction. So why is this particular feature of Minkowski spacetime relevant? The fact that it admits this thing called a bifurcate Killen horizon. The bottom line is going to be a spacetime with a bifurcate Killen horizon decomposes into 4 regions, right, with respect to the Killen horizon, and admits 2 distinct time-like Killen vectors, at least with respect to the right and left wedges. Right? So in the right wedge, and in the right wedge, we have 2 time-like Killen vectors, right? The generator of eta time translations and also the generator of time translations in the inertial t-coordinate direction. So that's a feature of Minkowski spacetime that, as we'll see, is also a feature of the 2 wormhole spacetimes that I'd like to review. Okay, so that's how to view Minkowski spacetime as an extension of a smaller spacetime. Right? And to wrap up this warm-up exercise on Minkowski spacetime, let's now be reminded of the notion of a conformal diagram, right, which is going to pop up again in descriptions of wormhole spacetimes. So conformal diagrams, right, were introduced by Roger Penrose. Sometimes they're called Penrose diagrams. And his goal was to construct a diagram, a space-time diagram, in which various infinities that cannot be represented in a normal space-time diagram can be represented in this particular diagram. Right? So with respect to Minkowski spacetime, right, intuitively, there are 3 types of infinities. If you go far enough along a time-like curve, you reach time-like infinity. If you go far enough along a space-like curve, you reach space-like infinity. And if you go far enough along a null-like curve, right, you reach null-like infinity. So how can we represent these 3 types of infinities in a finite spacetime diagram? So Penrose's intuition was, I take it, to just identify an appropriate set of coordinates that allow you to transform coordinates that perhaps have an infinite range to new coordinates that have a finite range. Right? So one example of a mathematical function that accomplishes this is the inverse tan function. Right? It maps its argument's range, infinite range, x can range from -infinity to infinity, plus infinity, to a finite range of y values, right? Minus pi/2 to plus pi/2. And so with that example in mind, right, we can introduce what we might call Penrose coordinates for Minkowski spacetime, call them capital T prime, capital R prime, related to inertial coordinates or spherical coordinates TR by this inverse tan function. Right? In particular, take the sum and the difference of these new Penrose coordinates and relate them to the sum and differences of the old coordinates by this inverse tan function. And it turns out that's enough to restrict the ranges of the new coordinates to finite ranges. Right? Whereas the old little t coordinate ranged from -infinity to plus infinity, the new Penrose capital T prime coordinate has a finite range. And where the original little radial coordinate ranged from 0 to plus infinity, the new coordinate capital R prime has a finite range. Right? And now we can express the Minkowski interval in these new coordinates, Penrose coordinates, and it takes this form in the second brown box. Right? So it looks almost identical to the Minkowski interval in spherical coordinates, except for this prefactor term out in front, right? 1 over the square of cosine capital T prime plus cosine capital R prime. And it turns out it's this prefactor encodes all the places where the original coordinates blew up, went to infinity. Right? So for various values of capital T prime and capital R prime, the prefactor diverges. And it's and it's at those values that correspond to infinite values for the original coordinates. So Penrose's idea was then to write down the space-time interval for a distinct space-time, a space-time that's distinct from Minkowski space-time, but that is conformally equivalent to Minkowski space-time, right? So call the space-time interval for this new space-time ds squared tilde, right? And all Penrose has done is he just removed the prefactor term, right? So this new space-time, its metric is conformally equivalent to the Minkowski metric. It only differs by this factor. And that's roughly the definition of two metrics that are conformally equivalent. Now, if we and then his idea was to take these points at infinity in Minkowski spacetime and represent them as points on the boundary of this new conformally equivalent spacetime. And the result in terms of an ordinary spacetime diagram is hopefully this familiar diagram called the conformal diagram or Penrose diagram for Minkowski spacetime, right? In it, all these various infinities associated with Minkowski spacetime are represented in the diagram itself, right? So little I superscript plus and superscript minus represent future and past time-like infinities in Minkowski spacetime. I naught represents space-like infinity, and these two surfaces, scri plus and scri minus, represent future and past null infinity. So that's, again, the conformal diagram for Minkowski spacetime. Okay, so with Minkowski spacetime in hand, let's now move on to the first example of a wormhole spacetime in general relativity. This is what I'll refer to as extended Schwarzschild spacetime. And to get extended Schwarzschild spacetime, let's of course first start with Schwarzschild spacetime. So it is the unique spherically symmetric vacuum solution to the Einstein equations with spacetime interval and spherical coordinates given by this expression. So you might notice that this is formally similar to the Minkowski interval in spherical coordinates, except for these two prefactor terms out in front of the temporal and radial terms, right? And both of these factors involve a constant R sub s. Here are 4 properties of this Schwarzschild interval. And these properties are going to help us formulate an interpretation of Schwarzschild spacetime. So the first property is the following: for values of the radial coordinate much greater than, if you have any questions, please don't hesitate to interrupt. For values of the radial coordinate greater than this constant R sub s, it turns out the constant can be approximated by this value 2gm, where g is the Newtonian gravitational constant, and m is the mass of a spherically symmetric mass. And the justification for that is, it turns out in this range of the radial coordinate, if you derive the geodesic equation associated with this interval, it takes the form of Newton's second law for force due to the gravitational field of a spherically symmetric mass, capital M. A second feature, a property of the Schwarzschild interval, is that it diverges, right, at the value of the radial coordinate r equals 0. In both the prefactor terms, right, in front of dt squared and dr squared, when r is 0, they diverge. And this is called a physical singularity because if you calculate this particular scalar invariant, you get a function that's inversely proportional to r to the 6, right? So when r is 0, this scalar invariant diverges. And you get this observable by taking the Riemann curvature tensor associated with the Schwarzschild metric and then contracting all of its indices. And that's supposed to give you a scalar quantity that's an invariant insofar it's the same. It takes the same form it takes the same values in any coordinate system. It's independent of your coordinate system. So that's referred to as a physical singularity. Then there's another place where the Schwarzschild interval diverges, right? And it's at the value of R equal to R sub S. So I guess it's the second term that diverges when R equals R sub S. And this is called a coordinate singularity because it turns out there's no corresponding divergence in a curvature scalar. So this indicates that this divergence perhaps is a feature of the particular coordinate system we chose to express the interval. And then finally, at R equals R sub S, we have the signature of the metric changes. So roughly the signature of the metric is given by the signs in front of the temporal term in the interval and the spatial terms in the interval. Right. So in the convention that I've adopted, the temporal term gets a minus sign and the spatial terms get a plus sign. So notice that for R greater than R sub S, that convention stands, right? There's a minus sign in front of the temporal term and a plus sign in front of the radial and spatial terms. But for R less than R sub S, the signs change, right? And that suggests that for R less than R sub S, the radial coordinate behaves like a temporal coordinate. Right? It now has the minus sign in front of it. And that indicates that within R, the region R less than R sub S, future directed time-like and null curves eventually are going to hit the physical singularity at R equals 0. If you just follow them along as the R coordinate decreases. And that in turn entails that at least under one understanding of the event of an event horizon, the surface R equals R sub S can be identified as an event horizon. Namely, it's a surface beyond which future directed time-like and null curves cannot escape to infinity. So these properties then suggest interpreting Schwarzschild spacetime as the spacetime associated with a black hole. Under the understanding of a black hole, if we understand a black hole to consist of a physical singularity, right, separated by an external spacetime by an event horizon. Okay. Now, in typical presentations, right, of Schwarzschild spacetime, we now are asked to focus on this coordinate singularity issue. How do we get rid of this coordinate singularity? Right? And the idea is going to be that we need to identify an appropriate coordinate system in which this coordinate singularity essentially vanishes. Right? We just need to switch to a new coordinate system. And ultimately, as we'll see, the coordinate system that we end up with is going to be associated with this extended version of Schwarzschild spacetime, what's called extended Schwarzschild spacetime. So here's sort of the standard way of getting rid of the coordinate singularity in the Schwarzschild spacetime interval. So we're first asked to focus on the behavior of radial null curves. Radial in the sense that we hold the angular coordinates constant, and null in the sense that we require the spacetime interval to be 0. If you substitute those constraints into the Schwarzschild interval and solve for the ratio of dt over dr, you get this nice expression on the right. So essentially, this is an expression for the slope, right, of a radial null curve, and by extension, it's the slope of a light cone defined by a bunch of radial null curves. And then we see that for values of the radial coordinate much greater than R sub s, we get nice behavior for the slope of radial null curves. For the behavior of light cones, the slope is just plus minus 1. Light cones are 45 degrees, given an appropriate adoption of units. But as we approach the event horizon, right, the slope goes to infinity, plus or minus infinity. The light cones close up. Right? So how do we deal with this initial problem? So the suggestion is to pick coordinates so that the slope of a radial null line, low curve, is always has this nice feature. It's always plus or minus 1. So we require of any coordinate system that we pick, the temporal coordinate should equal plus or minus the radial coordinate up to an additive constant. And the initial attempt to enforce this constraint produces this thing called a tortoise coordinate, R sub star, right? So we might initially attempt to enforce this requirement by simply solving for t as a function of r in this equation for the slope of a radial null curve, and then identifying in the resultant expression, identifying that part that is independent of this of an additive constant with a new radial coordinate, this r sub star thing, and that automatically enforces this constraint. So in the new coordinate system consistent of the old t coordinate and this new tortoise coordinate r star, the slope of radial null curves is nice, right? Plus or minus 1. The problem, though, is individually the t coordinate and the tortoise coordinate diverge as we approach the event horizon. So whereas the ratio is nicely behaved, independently they are badly behaved. So the next step then is, well, let's try to come up with a coordinate system that addresses this problem once and for all. And it turns out this set of coordinates, what are called null Kruskal coordinates, UV, finally solve both of these issues. Right? So the U and V coordinates are defined roughly by exponentiating, right, the difference in the sum of the tortoise coordinates. And they're referred to as null coordinates insofar as curves of constant U and V are null curves. So it turns out if you express the Minkowski interval in null Kruskal coordinates, we no longer get a divergence at the value that corresponds to r equals r sub s. In this case, it's uv equals 0. So our problem is solved. We've gotten rid of the coordinate singularity, but at the expense of these null coordinates, right? Null coordinates are useful in certain circumstances, but naively, right, it's hard to determine what the temporal direction is and what the spatial directions are if you're using null coordinates. So that suggests we move to yet another system of coordinates. And this is the final system we're going to consider. So these are called, we can call these Kruskal coordinates, capital T, capital R. And their relation to null Kruskal coordinates is fairly simple, right? The Kruskal time coordinate is just the sum of the Kruskal null coordinates, and the radial coordinate is the difference. And so at the original coordinate singularity corresponded to the null curves in Kruskal coordinates now have this, are now characterized by this nice feature, right? They now have, they preserve this invariant feature of the slope of their slopes, plus or minus 1. The original coordinate singularity is now given in Kruskal coordinates by capital T equals plus or minus capital R. The physical singularity in Kruskal coordinates is given by capital T equals plus or minus square root of 1 plus R squared. And the exterior region in the Kruskal coordinates now corresponds to two ranges, right? Capital R much greater than capital T and capital R much less than capital T. And it turns out, again, if you express the Schwarzschild interval in Kruskal coordinates, there's no divergence at the original coordinate singularity in the old coordinates, right? That's T equals plus or minus R. But one feature of Kruskal coordinates, well, now we have coordinates in which, right, there's a time direction and a spatial direction. On the other hand, it looks like, right, all the constraints on Kruskal coordinates corresponding to the constraints on the left that define these features of Schwarzschild, our original Schwarzschild spacetime, are produced twice, right? They correspond to two constraints on Kruskal coordinates. So this is an indication that Kruskal coordinates cover our original Schwarzschild spacetime twice. And that suggests we can view Schwarzschild spacetime as a region, a wedge, as it turns out, in a larger spacetime that we might call extended Schwarzschild spacetime that is covered once over by our Kruskal coordinates. So again, the analogy is with the Minkowski case, right? Just as we can view Minkowski spacetime as an extension of Riddler spacetime, so we can consider the spacetime covered by Kruskal coordinates as an extension of Schwarzschild spacetime. And the extended Schwarzschild spacetime interval in Kruskal coordinates takes this explicit form. All right. So again, just as we can view Minkowski spacetime as an extended version of Riddler spacetime, similarly, extended Schwarzschild spacetime can be thought of as an extension of Schwarzschild spacetime. So here's a diagram, a space-time diagram of extended Schwarzschild spacetime and Kruskal coordinates, capital T, capital R. Again, I'm suppressing the angular coordinates for simplicity. It's similar to the spacetime diagram of Minkowski spacetime. It's divided into four regions. One glaring difference, of course, is the presence of this physical singularity in extended Schwarzschild spacetime. It's represented by the red hyperbola, right, at the top and the bottom. And in this case, the right wedge, region 1, can be identified with Schwarzschild spacetime. In Schwarzschild spacetime, and again, it's in complete analogy with the Minkowski case, curves of constant little r, right? That's the original radial coordinate for Schwarzschild spacetime, have these three properties. Their hyperbola, capital R squared minus capital T squared equals constant in Kruskal coordinates with asymptotes at capital X equals plus or minus capital T, right? These two dashed lines. They're orthogonal to little t equals constant surfaces, which again form Cauchy surfaces in Schwarzschild spacetime, and the complete family of such surfaces form a foliation of Schwarzschild spacetime. And thirdly, curves of constant little r turn out to be integral curves of the generator of translations in the little t direction. And in complete analogy with Minkowski case, this is a time-like Killen vector that's distinct from another time-like Killen vector in region 1, given by the generator of translations in the Kruskal time direction. And just as in Minkowski spacetime, so in extended Schwarzschild spacetime, the event horizon, in this case, the event horizons, right, given by the dash lines, capital R equals plus or minus t, form a bifurcate Killen horizon, in this case, generated by the generator of little t translations. So that's extended Schwarzschild spacetime considered as an extension of Schwarzschild spacetime with properties that are analogous with the properties of Minkowski spacetime. All right, but one disanalogy, of course, is the presence of the physical singularity, right, in extended Schwarzschild spacetime. Well, so the next step now is going to be how we can interpret extended Schwarzschild spacetime as represented in a wormhole, right? So the idea is going to be, we're going to look at capital T equals constant spatial slices through extended Schwarzschild spacetime, and consider the extent to which these capital T equals constant slices can be thought of as in some sense represented in a wormhole that connects regions 1 and 4. First, let's consider the particular capital T equals constant slice for capital T equals 0, right? Let's consider its geometry in terms of the original spherical coordinates. And moreover, we're going to set the theta coordinate equal to pi over 2 for simplicity. So substitute these constraints into the Schwarzschild interval for simplicity, and we get this expression. So this is the interval for a two-dimensional surface, right? And to visualize it, let's embed it in a three-dimensional embedded Euclidean space, right? So here's the interval in cylindrical coordinates for a three-dimensional Euclidean space. To embed our two-dimensional surface into the three-dimensional Euclidean space, let's equate the coefficients in front of the dr squared terms, and then we can solve for the z coordinate as a function of r. And we get this expression. The phi term drops out, right, in this case. And then we can re-express the radial coordinate as a function of the z coordinate. And we get this equation down here at the bottom. And that turns out to be the equation of a parabola in the RZ plane, right? It's represented by this blue curve in the diagram on the right. It intersects the r axis at r equals r sub s. Now to regain our original two-dimensional surface, we have to restore the phi dimension that dropped out here. And the way to do that is just to take our parabola and rotate it about the z-axis by 2 pi. And the result is this two-dimensional surface that is referred to as a paraboloid of revolution, I believe. Right? So that's supposed to be a representation of the capital T equals 0 spatial slice in extended Schwarzschild spacetime. So let's consider a number of other T equals constant slices. Right? So on the left here is, again, a diagram, a spacetime diagram of extended Schwarzschild spacetime. And I've represented, so I'm taking this diagram from, I think this is from Sean Carroll's textbook on relativity. So on the right, on the left is a spacetime diagram of extended Schwarzschild spacetime, where we've represented 5 capital T equals constant spatial slices. Right? The T equals 0 spatial slice that we just looked at is the C slice in this diagram. Right? And all of these slices have the geometry, the spatial geometry of a paraboloid of revolution. So the C slice, the capital T equals 0 slice, has the greatest minimal cross-sectional area given by 4 pi r sub s. Right? The B and D slices have minimal cross-sectional area 4 pi r, where r is less than r sub s. And notice that the A and E slices are disconnected because they intersect the physical singularity. Right? So this representation of the spatial slices, actually the capital T equals constant spatial slices of extended Schwarzschild spacetime suggests an interpretation in terms of a wormhole. Right? So we might think of the wormhole at an instant as represented by any of these T equals constant spatial slices of extended Schwarzschild spacetime. And we might define the wormhole's throat as the region of a given spatial slice between the left and right event horizons. Right. So for the C slice, there really is, it has a trivial throat. Right. There's no region interior to the event horizon contained in the C slice. So if you're following along the C slice from region 1, you go through the event horizon, right, at this thing called the bifurcation surface, and then immediately you exit the event horizon into region 4. Right. There's no region, subregion of the C slice that's wholly within the event horizon. On the other hand, the B and D slices do have subregions contained within the interior region of the event horizon. In the D slice, we have this green region that might be identified as the wormhole throat. In the B slice, we have this red region. Right? And the A and E slices also have wormhole throats, but again, they're disconnected. Okay. So, and of course, right, there is this historically, this article from 1935 by Einstein and Rosen, in which they suggest that these spatial slices through what we're calling extended Schwarzschild spacetime can be thought of as a bridge that connects these two disconnected regions, region 1 and region 4. So that's the wormhole interpretation of extended Schwarzschild spacetime. All right, so now let's again remind ourselves of what the conformal diagram for extended Schwarzschild spacetime looks like. So again, in analogy with the case of Minkowski spacetime, we can pull in, right, the various types of infinities associated with extended Schwarzschild spacetime into a finite diagram. If we just switch to a new set of coordinates, let's call these Penrose coordinates. Of course, they're different from the Penrose coordinates from Minkowski spacetime. Let's call them capital T double prime and capital R double prime. But right, the method is the same. We're going to relate them to the Kruskal coordinates using this inverse tan function in this way, and that effectively guarantees that the ranges of the double prime coordinates are finite. And in these new Penrose coordinates for extended Schwarzschild spacetime, we can, right, represent these various features of Schwarzschild spacetime. Right, the singularity at r equals 0. If you go through the coordinate transformation to Penrose coordinates, is represented by 2 straight lines. Recall that in the original Kruskal coordinates, it was represented by 2 hyperbola. So the details here just involve applying some identities from trigonometry to the relations that the Penrose coordinates satisfy. And then you can also show that the event horizon represented in Kruskal coordinates by capital P equals plus or minus R is represented in these new Penrose coordinates by the same expression. Capital T double prime equals plus or minus capital R double prime. So this indicates that the event horizon in these new coordinates is represented again by straight lines, as it is in Kruskal coordinates. And then the third feature here is these Penrose coordinates preserve the invariant light cone structure of the Kruskal coordinates. Right? All light cones are at 45 degrees with respect to an appropriately chosen system of units. The slope of radial null curves is plus or minus 1. So all of these properties then can be represented in a space-time diagram, right? So here's the conformal or Penrose diagram for extended Schwarzschild space-time. The physical singularity is represented in these Penrose coordinates by these two straight lines, red straight lines, or surfaces if we add back the angular coordinates, right? The event horizon is represented by these two dashed lines. The space-time is still separated into 4 regions, right? The 2 exterior regions are 1 and 4, and then we have these 2 interior regions, interior to the event horizon, 2 and 3. All right. So that's extended Schwarzschild space-time, right? The first example of a wormhole space-time in general relativity. So with that example in hand, we can now move on to a second example of a wormhole space-time in general relativity. And this is what we might call extended ADS Schwarzschild space-time. And as you might imagine, to get extended ADS Schwarzschild space-time, we first have to consider ADS Schwarzschild space-time. And to get a grasp on ADS Schwarzschild space-time, let's first begin with ADS space-time. Question?
Yeah, I just wanted to ask, so just a quick clarification and then a more substantive question. So the clarification is, so in the, let's say in the Kruskal-Sekres coordinates, or if I want to consider an astrophysical black hole, then is it right that I'll just take the top right quadrant?
Yeah. So this diagram, sometimes this diagram is interpreted as an eternal black hole, right?
Yeah.
And to get a black hole, to represent a black hole that perhaps is the result of gravitational collapse of some gravitated mass. Yeah, so the diagram, you'd have to include the world line of the gravitated mass in the conformal diagram, and it effectively cuts off regions 3 and 4.
So this is the same in the previous diagram as well, the KS diagram, right? Not the Penrose diagram, but the
right, the space-time diagram in Kruskal.
Yeah.
Mm-hmm.
It's the same, so it's just the top right quadrant is the okay. Thanks. And the second thing is, you mentioned, the Schwarzschild space-time we now know is motivated. We can sort of tell some physical story of how something like Schwarzschild space-time can come about by collapse of stars. But with these extended space-times, that's at this point we don't know any physical process that could lead to this full extended space-time, right? It's just we can write these coordinates out to these regions and we think there might be something there, but there's no physical reason we think there's something there. Is there?
I think that's right. Yeah. I mean, so as we'll see, right, one interpretation of the conformal diagram for extended ADS Schwarzschild space-time, eventually Maldacena and Susskind suggested it represents 2 entangled black holes. So I mean that's a physical system, right? But whether or not such a physical system exists is a different question. But in other words, I mean, you can come up with physical interpretations of, say, this thing called an internal black hole.
I see. Okay, but I guess the process leading, right? We have a very good understanding of how astrophysical black holes form. We don't really have a very good understanding of how those entangled black holes combine to create these kinds of spacetimes, right?
Yeah, that's a fair statement.
Okay, thank you.
Okay, so here is the space-time interval for ADS spacetime in spherical coordinates, right? It's the unique vacuum solution to the Einstein equations with constant negative curvature. And in form, right, it's similar to the Minkowski interval in spherical coordinates, except for, again, these prefactors in front of the dt squared and dr squared terms. And they're different, right, from the case of Schwarzschild spacetime. So here they involve, the second term involves a constant little a, which is the radius of curvature of ADS spacetime. And as it goes to infinity, the ADS interval becomes the Minkowski interval. Right? And that's ADS spacetime. To get ADS Schwarzschild spacetime, at least mathematically, it requires just a slight modification to the ADS interval. So ADS Schwarzschild spacetime is the unique spherically symmetric vacuum solution to the Einstein equations with constant negative curvature and interval and spherical coordinates given by this expression. Right? We've just added this middle term to the two prefactors in the ADS interval. So for large R, right, the ADS Schwarzschild interval becomes the ADS interval. Right? For large R, the middle terms in these two prefactors drops out. On the other hand, for small r, the last term drops out, and the ADS Schwarzschild interval becomes the Schwarzschild interval. And just as the Schwarzschild interval in spherical coordinates has a coordinate singularity, in that case, it was at r equals r sub s. The ADS Schwarzschild interval also has a coordinate singularity at a value of r, but not r sub s. It's that value, call it r sub h, that solves this expression, right? Just take the prefactor inside the parentheses and set it to 0, solve for r. That value of r makes this interval blow up. Really, it makes the radial term blow up. And again, in analogy with the Schwarzschild case, we can get rid of this coordinate singularity by adopting an appropriate set of coordinates, right? Then the analog of Kruskal coordinates in the Schwarzschild case. So we can transform to Kruskal-esque coordinates to get rid of the coordinate singularity in a light cone invariant way, right? So the new coordinates are chosen so as to preserve the invariant nature of the light cones. And just as with extend and the space-time we get as a result, right, can be thought of as an extension of ADS Schwarzschild space-time, in the same way that the space-time that's completely covered by Kruskal coordinates can be thought of as an extension of Schwarzschild space-time. And similarly, we can adopt a wormhole interpretation of extended ADS Schwarzschild space-time in terms of constant t slices, right? Where t in this case are these Kruskal coordinates adapted to ADS Schwarzschild context. And of course, we can construct a conformal diagram of ADS Schwarzschild spacetime, extended ADS Schwarzschild spacetime. In this case, it looks like this. It turns out the physical singularity is represented in the appropriate Penrose coordinates by a hyperbola, not by a straight line. Extended ADS Schwarzschild spacetime has a boundary at r equals infinity, which is, I think, in this case, it's time-like. Right, here's the event horizon at r equals r sub h. You can show that it also defines a Befrichet Killen horizon. It divides the spacetime into four regions: 2 exterior and 2 interior. All right, so to step back, we've now looked at 3 examples of spacetimes that we can interpret as extended spacetimes of smaller spacetimes, roughly, right? Minkowski SpaceTime as an extension of Riddler SpaceTime, and then these 2 additional examples: extended Schwarzschild spacetime, extended ADS Schwarzschild spacetime. In the last column, right, Minkowski spacetime does not admit an interpretation in terms of a wormhole, whereas the other 2 cases do. So far, this is just general relativity, right? General relativity, 3 solutions to the Einstein equations, 2 of which admit interpretations in terms of wormholes. So the next question is, what do these spacetimes have to do with quantum entanglement? Because ER equals EPR relates wormholes to entanglement. The story to come is going to be for all 3 of these examples, the vacuum state of a quantum field in the extended spacetime can be expressed as an entangled state across the left and right wedges. So that's one way of relating entanglement with spacetime structure. And the second part of the story to come is we'll end the story with Maldaceno's example, in which he reinterpreted the entangled state associated with case C as an entangled state in a boundary CFT. Right, so he's going to introduce an ADS CFT element into this account of how states of a quantum field in a background spacetime can be expressed as entangled states. All right, so that's the end of the first part. I'd like to move on now to the second part of the lecture. Again, this is a review of quantum entanglement and how it relates to spacetime structure. And the context is going to be quantizing a field in a background spacetime. So we're first going to review the standard procedure for quantizing a field in Minkowski spacetime. And then, roughly by analogy, we'll see how that translates into quantizing a field in extended Schwarzschild spacetime. Right? The big difference between these spacetimes is, right, extended Schwarzschild spacetime is a wormhole spacetime. All right, so quantum entanglement in Minkowski spacetime. The claim that I'd like to consider is the following. The vacuum state of a quantum field in Minkowski spacetime can be expressed as an entangled state over the left and right Riddler wedges, right, the blue regions in the spacetime diagram of Minkowski spacetime. And there are at least 3 routes to such a demonstration of this claim. A question?
Yeah, sorry, perhaps after, because it's a clarificatory question for the previous construction. So perhaps once you are done with this, so I may go back. So no, but the thing is that given the previous question, so just a general remark, I mean, one should keep a critical look at this wormhole construction to begin with, because I mean, it's a fact in the physical community that this is controversial. For one thing, because okay, the idea comes from basically getting rid of this singularity in Schwarzschild spacetime. Okay, but it's not entirely clear to what extent. I mean, just adding this additional set of coordinates, crucial in this case, actually adds any physically meaningful. And the thing is, just to link with the previous question about black holes. I mean, the problem is that, for instance, in several approaches to quantum gravity, I mean, there is a clear dynamical reason why basically no singularity emerges at all. So in that sense, basically, it's not like just a sort of mathematical artifact in the sense that just defining a set of coordinates that, okay, gets rid of the initial singularity and thwarts it, but by no means means that that new set of coordinates represents anything physical. Whereas in different approaches, this singularity basically is avoided altogether by the very dynamics of the theory. So in that sense, for instance, in black holes, I mean, there are some proposals. Of course, I mean, this is beyond any observational side so far, but okay, there are promising proposals that the singularity within a black hole can be avoided. And this is what's in the literature are called Planck stars. Anyway, my point is just before moving to this EPR sort of conjecture, which, okay, fair enough. I mean, one should keep a critical attitude regarding the very construction of a wormhole. So, but okay, it was just a general remark. I mean, to have in mind, because well, I think it's a clash between different attitudes in theoretical physics regarding those basically coming from higher physics inspired string theory and those basically coming from canonical approaches to quantum gravity. This is something that it's very general clash in attitudes to several problems. So okay, so that was just my general remark.
Okay, but so the idea is that so this is sort of a mathematical construction, right? It's physical in the sense that it is a solution to the Einstein equations, right? But again, so is your remark concerning, right?
Yes,
well, it's a mathematical solution, but what the extent to which it's a physically relevant solution might be.
Yeah, because in GR we also have closed loops, and that doesn't mean that we have Gödel spacetimes, which are, okay, strictly speaking, are mathematical solutions to Einstein equations, but basically it's quite unclear to take them as physically real. So that's basically the thrust of my remarks. So fair enough. I mean, one of course may have this understanding in terms of wormholes. I'm not saying it is, of course, anything to be discarded, because we are basically far from any reliable observations on either side, on basically singularity or avoiding altogether. But okay, just to have basically a piece of the big picture and what this wormhole becomes about. So, but okay, yeah. Thank you.
Yeah, fair enough. Yeah. So again, one attitude might be, these are highly idealized solutions to the Einstein equations. How seriously should we take them from a physical point of view? And by implication, how seriously should we take any hypothesis based on them, right? In particular, the ER equals CPR hypothesis. Yeah, I think that's a fair question. But so I'm going to push that question to the side and continue the, at least, so my goal here is to try to understand the motivations for the proposal in Maldacena and Susskind's original article. And yes, one criticism is, or one concern is how physically relevant should we take, how physically relevant is the proposal itself? Okay, but so to return to the exposition, so we'd like to demonstrate this claim about the vacuum state of a quantum field in Minkowski spacetime, right? Because there is a sense in which this is a way of at least initially understanding how entanglement might be related to space-time structure, right? And ultimately, as we'll see in Maldaceno's example, it's intimately connected to, in particular, the quantization of the field in his case, in ADS, extended ADS Schwarzschild spacetime. So there are at least three ways of attempting to demonstrate this claim, this specific claim. And the first, I think, may be more familiar to philosophers of physics than the second. So the first is we use the sort of standard canonical quantization procedure to quantize our field in Minkowski spacetime. And as I understand it, it consists of three steps. So we take our field, we take solutions to the relevant field equations, and we decompose them into negative and positive frequency modes. So we perform this mode analysis. And then in step two, we equip the space of positive frequency solutions with an inner product, and then complete it to form a single particle Hilbert space. And then in step three, we get a Fock space. We define a multi-particle Fock space in terms of these single particle Hilbert spaces. So that's sort of the canonical way of, in a nutshell, that's the canonical way of quantizing a field. And if we're doing it with respect to Minkowski spacetime, it turns out the first step can be done in the right Riddler wedge in one of two ways, right? To decompose the field into negative and positive frequency modes, implicitly requires a temporal direction. And we have two different temporal directions, roughly speaking, in the right wedge. Right? We have the temporal direction associated with the Riddler eta coordinate. So here's the generator of eta time translations, but we also have the time direction associated with the inertial little t coordinate. And it turns out if you go through these steps using the eta coordinate initially to split your frequencies, so to speak, then you obtain what's called a representation of the canonical commutation relations associated with your field that in the literature is called the Fulling representation. And it has a unique vacuum state. The convention is, this vacuum state is called the Riddler vacuum. On the other hand, if you go through this procedure using the little t coordinate initially, the representation of the canonical commutation relations you get as a result is called the Minkowski representation with corresponding unique vacuum state called the Minkowski vacuum. And then you can then show, and it takes a fair amount of lines to show this, but standard presentations of quantizing a field in Minkowski spacetime ultimately lead to this expression. The claim here is, so let H, L, and HR be one particle Hilbert spaces with respect to the left and right Riddler wedges, degrees of freedom supported in the left and right Riddler wedges. Now restrict the Minkowski vacuum to the right Riddler wedge. And then it turns out the claim is you can then express the restriction of the Minkowski vacuum to the right Riddler wedge in terms of an entangled state over the left and right wedges, right? Where n sub L and n sub R are eigenstates of energy in the left and right wedges. And in this expansion coefficient term, beta takes this particular form, 2 pi divided by kappa, where kappa is the surface gravity of the Killing horizon. So here's an expression that explicitly, right, describes the vacuum state of a quantum field in Minkowski spacetime as an entangled state across the left and right wedges. But in the philosophy of physics literature, it's been pointed out that this expression as it stands is mathematically ill-defined from kind of a rigorous point of view. These two representations of the canonical commutation relations, the Fullen and the Minkowski representations, are unitarily inequivalent. There's no isomorphism between them, roughly speaking. And this has been pointed out in a number of articles. So that's if you'd like, if you'd like a rigorous demonstration of the claim that the Minkowski vacuum state is entangled across the left and right wedges, then this route gives you less than you might want. Now there's an alternative route, right? And this is the route that seems to be adopted in a lot of the physics literature on this subject. So in his Jerusalem lectures on black holes, Harlow describes this route. It's also summarized in an article by Ted Jacobson and in Hartman's lectures. So this is the Euclidean path integral route towards demonstrated entanglement of the vacuum state of a quantum field in Minkowski spacetime. So as I understand it, it involves these three steps. So the first step, we express the overlap between the Minkowski vacuum and some field configuration state as a Euclidean path integral that depends on Euclideanized time, right? Where T sub e is just I times little t. And then in the second step, we change variables in our path integral. We switch from Euclidean T sub e time to Euclideanized eta time. And remember, eta is the Riddler time coordinate, and eta sub e is just I times eta. And we change our field configuration variable to those appropriate, those with that associated with left and right wedges. So in the physics literature, this is sometimes described as a trivial, quote unquote, change of variables. It's the same integral, we're just switching our variables. And then in the third step, we re-express the so transformed integral as a transition amplitude. And then we massage that transition amplitude into the form in which on one side is an expression for the Minkowski vacuum, and on the other side is an entangled state over the left and right wedges. So here's my understanding of how these three steps pan out. So in the first step, right, the idea is we begin with the overlap between the Minkowski vacuum and this field configuration state, and ultimately we want to express it as a Euclidean path integral. But there's this intermediary step where we represent the Minkowski vacuum as the limit as Euclidean time goes to infinity of a Euclidean time evolved arbitrary field configuration state. And there are at least two arguments that attempt to justify this way of representing not just the Minkowski vacuum state, but any vacuum state. Right? So in the first argument, the idea is that Euclidean time evolution damps out excited states. Right? So in normal time evolution, the time evolution operator is e to the minus I times t times h. H is the appropriate Hamiltonian, right? The generator of time transformations. And if we take t to infinity in e to the minus I th, we get this oscillating behavior. But if we absorb the I into this definition of Euclidean time, there's no longer an I in the exponent. We have this nice dampened behavior, right? So e to the minus te h, as te goes to infinity, the exponent goes to 0. So regardless of what chi is, if we Euclidean time evolve it long enough, all its excitations damp out and we get the vacuum state. So that's one argument. Another argument I've seen is the following. At finite temperatures, Euclidean time can be interpreted as 1 over the temperature. And if you adopt that attitude, then large Euclidean time states correspond to low temperature states. Right? And in the limit, as T goes to infinity, we get the lowest temperature state, i.e. the vacuum. So that's the intermediary state, right? We now have this transition amplitude that we can now express as a path integral, right? And the path integral is over field configurations between some initial configuration, chi, at Euclidean time minus infinity, to some final configuration, phi, at Euclidean time equal to 0. Right? It's an infinite range, and we're starting at minus infinity because, in a sense, we're preparing the Minkowski vacuum by time evolving this arbitrary state in Euclidean time. So it's a path integral between initial and final field configuration states in the lower half of Euclidean spacetime, minus infinity less than T sub e less than 0. So that's the first step. And then in the second step, right, involves this so-called trivial change of variables. So here's a space-time diagram of Euclidean space-time. Our path integral is over the lower half of Euclidean space-time, right, from T equals minus infinity up to the surface T equals 0. We then observe that the lower half of Euclidean spacetime is covered by this foliation of eta E equals constant surfaces. So we can integrate over the lower half of Euclidean spacetime by beginning with some eta E equals constant surface in the left wedge. That would be eta E equals pi, and integrate it over all eta E equals constant surfaces to finally get to the eta E equals 2 pi constant surface in the right wedge. And we still are integrating over the entire lower half of Euclidean spacetime. But now we're disintegrating over different variables, time variables. Right? And if we're going to switch to eta E variable, we also have to change our field configuration variables. So now the initial configuration variable should be some configuration supported in the left wedge, call it phi L, and the final variable should be some configuration supported in the right wedge, call it phi R. And then I guess we have to add this CPT antilinearity map between HL and HR to make sure that the configuration variables are associated with the same Hilbert space. So assumedly a trivial change of variables. And then step 3, we're now going to re-express the path integral on the right back as a transition amplitude, right? So it corresponds to the transition amplitude between some initial state phi L and some final state phi R, and we're time evolving phi L using this operator between eta equals pi and eta equals 2 pi. So we get the factor of pi there. And the Hamiltonian we're using here is what's called the boost Hamiltonian, the Hamiltonian associated with the eta coordinate, eta E coordinate. So here's the claim is here's the transition amplitude associated with the path integral after the change of variables. Now you can insert a complete set of states and take advantage of the antilinearity property of the capital theta operator. And eventually we get this line, the second to last line at the bottom of the slide, which relates the original quantity we started with, right? The overlap between the Minkowski vacuum and the phi state with this weighted sum of overlaps between our left and right field configuration states, and in this case, energy eigenstates of the boost Hamiltonian. And the very last step involves, right, roughly, we're lopping off the bras on either side, right, the field configuration states. And again, we're left with this expression for the Minkowski vacuum in terms of an entangled state over the left and right wedges. But again, right, if you're rigorously minded, I think you might find this very last step a bit problematic, because it suggests that we're equating two states that belong to unitarily and equivalent representations of the canonical commutation relations, right? And that, from a rigorous point of view, is problematic. So stepping back, right? I think the authors who advocate this approach observe that one advantage of it is we did not have to assume the field that we're quantizing was a free field. And it turns out that's an assumption you have to make in the canonical quantization approach, route one. On the other hand, it does seem to look like this path integral approach still faces this problem from the rigorous point of view, this problem of unitarily and equivalent representations. So how to address this? Well, so what do we have? What can we say about this claim about the vacuum state of a quantum field, the Minkowski spacetime being entangled across the left and right wedges? Here are some options, and I'm going to call these options just the third route, right? So if you're concerned about this issue of unitary inequivalence, then one way to address it is to insert a cutoff into your field theory, right? And thereby turning it, transforming it from a theory with an infinite number of degrees of freedom to one with a finite number. And it turns out in a quantum field theory with a finite number of degrees of freedom, all representations of the canonical commutation relations are unitarily equivalent. So there's no problem of unitary inequivalence in theories with a cutoff. Alternatively, there are these really abstract, rigorous results you can prove, for instance, in algebraic quantum field theory involving the Riesch-Schlieder theorem that lets you claim, make a general claim about vacuum entanglement of a quantum field across arbitrary space-like separated regions. So in any event, right, this claim, specific claim about the vacuum state of a field in Minkowski spacetime being entangled across the left and right wedges probably can be made more rigorous if you so desire. All right, that's quantum entanglement in Minkowski spacetime, quantum entanglement in extended Schwarzschild spacetime. The claim is similar, right? The claim now is the vacuum state of a quantum field in extended Schwarzschild spacetime can be expressed as an entangled state over regions 1 and 4, right? The two wedge regions. And there's a quick and dirty argument that supports this claim, which is based on the observation that near the event horizon, Schwarzschild spacetime, at least the Schwarzschild interval, is formally identical to the Riddler interval. So near the event horizon, you might claim since we can express the Minkowski vacuum as an entangled state, similarly, we can express the correlate of the Minkowski vacuum in extended Schwarzschild spacetime as an entangled state over the correlates of the left and right Riddler wedges. So the correlate of the Minkowski vacuum state in extended Schwarzschild spacetime is this thing called the Hartle-Hawken vacuum state. It's this vacuum state associated with the Fock space built on the Kruskal time, big T coordinate, right? As opposed to the correlate of the Riddler coordinates, the original R and T coordinates, little r and little t coordinates. The the slight difference is the expression here for the Hartle-Hawken vacuum. In the expression, the constant beta takes a different value. All right. If you're not satisfied with that quick and dirty argument, right? Again, you're presented with a slightly more detailed argument involving these Euclidean path integral techniques. And in this case, the procedure is a little different than it was for the Minkowski case, insofar as in this case, the procedure is based on an argument that claims Euclidean Schwarzschild time is periodic, is cyclic. So I'm going to attempt to describe at least my understanding of what this means here, and perhaps in Johanna's lectures tomorrow, she might make this a bit more clear. So that's the first step, and then the second and third steps follow the steps in the Minkowski case. So here's the first step. How can we convince ourselves that in Euclidean Schwarzschild spacetime, the time coordinate is periodic? So let's first express the Schwarzschild interval in Euclidean time. Let's call this the Euclidean Schwarzschild interval, right? Here I'm suppressing the angular coordinates. And the only difference between this and the Schwarzschild interval is that we've absorbed the minus sign, right, in front of the temporal term into the definition of T sub E. Now we can introduce a new radial coordinate, call it rho, as a function of the original radial coordinate little r, and it turns out the Schwarzschild radius, this constant r sub s, in this way, and then you can show, then you can re-express the Euclidean Schwarzschild interval in terms of this new radial coordinate rho, and then look, and this is what it looks like initially, and then look, and then consider it in for the case in which the radial coordinate is roughly equal to r sub s. That just makes this prefactor out in front of the rho term identically 1, right? And then we get the interval for Euclidean Schwarzschild spacetime expressed in TE and rho coordinates in this form at the bottom. And that looks formally equivalent to the interval for a flat Euclidean space and polar coordinates, right? Where the angular coordinate theta is played by the ratio of TE over 2RS. And it turns out, right, the coordinate singularity at r equals r sub s occurs at rho equals 0. But if we treat TE as an angular polar coordinate, that allows us to treat the point rho equals 0 as the origin of our polar coordinates. So in these coordinates, we can treat the coordinate singularity at rho equals 0 as the origin of a two-dimensional Euclidean plane, provided we identify T sub E as an angular polar coordinate with a corresponding 2 pi period, or more precisely, TE over 2 times r sub s. Right? So that indicates Euclidean time is periodic in 4 pi r sub s. So here's a space-time diagram of Euclidean Schwarzschild space-time in well, I guess in the original R and Euclidean time TE coordinates, right? So Euclidean time is under the assumption that Euclidean time is periodic, right? So the origin is at r equals r sub s, the original coordinate singularity, and the lower half of Euclidean Schwarzschild spacetime is given by this shaded region, right? This is the region for t equals 0 to t equals 2 pi rs. So Euclidean Schwarzschild spacetime can be represented by this cigar diagram. So that's the first step. And then in the second step, right, and we go through this process of representing our vacuum state, in this case, the Hartle-Hawkins state, the overlap between the Hartle-Hawkins state and some field configuration state phi as a path integral by means of this intermediate step. Right? In this case, the path integral is still over the lower half of Euclidean of the corresponding Euclidean spacetime, in this case, Euclidean Schwarzschild spacetime, but now it's periodic, right, in TE. So the integral is from some initial configuration state at t equals 0 to some final configuration state at TE equals 2 pi rs. And then in the last step, right, we express this integral as transition amplitude, and then go through this process of massaging it into this second penultimate form, and then lop off the field configuration states on either side to get this final expression, right? That formally is identical to the expressions we got in the Minkowski case. One difference is, again, the value of the beta term. And again, from a rigorous point of view, there is this issue about, in this procedure, about moving from this second to last step to this last step. All right, so that's how to quantize a field in Schwarzschild spacetime, extended Schwarzschild spacetime. And now, right, the analogy now is, or the next step is to extend this procedure to quantizing a field in extended ADS Schwarzschild spacetime. And that turns out to be the subject of Maldaceno's example. His proposal that extended ADS Schwarzschild spacetime is dual to a particular entangled state in a CFT, namely this thermal field double state. So that's the last part of the lecture. So on first glance, right, this last example just seems to be a continuation of these other examples we just went through. We want to quantize a field in extended ADS Schwarzschild spacetime and express its vacuum state as an entangled state. But the new element is this appeal to the ADS-CFT correspondence. And it seems that there are two ways to view this new element. You might view it as an appeal to the ADS-CFT correspondence to justify expressions of this sort, right? Expressions of the vacuum state in terms of an entangled state. Alternatively, you might view Maldaceno's example as an appeal to previously established expressions of vacuum states in terms of entangled states to justify this additional entry in the ADS-CFT dictionary. In any event, right, the old claim seems to be this: the vacuum state of a quantum field in extended ADS Schwarzschild spacetime can be expressed as an entangled state over the two regions, 1 and 4. Under this new proposal, his new proposal is the following: under the ADS-CFT dictionary, extended ADS Schwarzschild spacetime is dual to a CFT thermal field double state. So what exactly is this thermal field double state? So here's a bit of context. For a given quantum field theory with some Hamiltonian H, with eigenstates little n, elements of some Hilbert space H, we can define what's called a thermal mixed state, right, rho, a density operator state given by e to the minus beta times the Hamiltonian, which can be expressed in this form, right? A weighted sum of projection operators onto each of the energy eigenstates, where beta is identified as 1 over the temperature. Now, to get a thermal field double state, the idea is to purify a given thermal mixed state. And this means we want to find a pure state of a larger system such that our thermal state is the reduced density operator for a given for a bipartition of the larger system into 2 subsystems. So the thermal field double state is the purification of a thermal state obtained by the following 2 steps. You first double the degrees of freedom of your initial Hilbert space H to form some product Hilbert space H1 cross H2, where H1 and H2 are copies of H. And then we want to construct a pure state, just call it TFD for thermal field double. That's an element of this larger product Hilbert space, such that the original thermal state can be obtained by tracing out the degrees of freedom of one of these subsystems from the projection operator the density operator corresponding to the thermal field double state. And the result right takes this form. If this is the form of the thermal state, mixed state, so we get an expression for the thermal field double state in terms of an entangled state, right, over these 2 Hilbert factor spaces, where the beta here is interpreted as 1 over temperature. Now, the way the thermal field double state is typically presented is that it's a state of a composite system, one of whose subsystems is some physical system that's in thermal equilibrium with a heat path that corresponds to the second subsystem. But formally, right, it looks like these expressions we've been more or less deriving, right, of the vacuum state of a quantum field in a background spacetime that emits a Bifurcat Killing horizon. So that's a thermal field double state. And then the final question is, what does this have to do with ADS-CFT? So here's the way I understand Maldaceno's proposal. 3 steps again. First, we take these 2 Hilbert spaces, H1, H2, right, associated with the thermal field double state as 2 copies of a conformal field theory. We then go through this routine that we've gone through a couple times already of expressing the overlap between, in this case, the thermal field double state and some field configuration phi as a Euclidean path integral over some appropriate spatial temporal region. Right? In the previous examples, instead of the thermal field double state, it was the Minkowski vacuum or the Hartle-Hawken vacuum, and the appropriate spatial temporal region was either the lower half of Euclidean spacetime or the lower half of Euclidean Schwarzschild spacetime. So do the same procedure for some perhaps arbitrary spatial temporal region. And then in the last step, use the ADS-CFT dictionary to identify a corresponding bulk spacetime. Right? So the idea is the spacetime region we're integrating over is roughly that region that kind of generates this TFT state. And ADS-CFT, and this TFT state is associated with 2 copies of a conformal field theory. In ADS-CFT, the conformal field theory lives on the boundary of some bulk spacetime, right? So if the boundary is given by the region that this path integral is is defined on, then the bulk spacetime should just be a bulk spacetime with this region as its boundary. So to put that, to represent that argument and using a bit of a few formula, right? Here's the standard procedure. We're representing the overlap between the thermal field double state and some field state in terms of a Euclidean path integral. Given the form of the thermal field double state, the range of Euclidean time that the integral is for the integral is t equals 0 to t equals beta over 2. And that depends on the particular form of the TFD state on the previous slide. And now we step back and look at this path integral. It's an integral over field configurations between starting at chi ending at phi on some spacetime region whose temporal part is given by this interval 0 to beta over 2. And according to the ISSPP differentiate dictionary, right, roughly we're asked to identify the spacetime that the CFT is defined on as the boundary of the spacetime that the ADS theory of gravity is defined on. Right? So if script S is given by the region that this path integral is defined on, then it's supposed to be the boundary of some spacetime, and it turns out that spacetime is it's the lower half of Euclidean extended ADS Schwarzschild spacetime. So I take it that's the connection that links ADS CFT with the procedures that we've been discussing so far. So Maldacena, this motivated Maldacena to suggest this particular entry. We might think of it as in the ADS CFT dictionary, right? On the left, we have extended ADS Schwarzschild spacetime, really ADS extended Euclidean ADS Schwarzschild spacetime, and on the right, we have this thermal field double state. Now, in Maldacena and Susskind's EPR, ER equals EPR article, they initially discuss this example, and they suggest there are two ways of understanding the duality here, or essentially two ways of understanding, in particular, the bulk spacetime and how it corresponds to the entangled state. The first interpretation they consider is under this correspondence, we have on the left a single black hole in thermal equilibrium, and on the right we have this original TFD thermal field double state. And it turns out this corresponds, well, there was this Hamiltonian, right, that appeared in this second step, right, in this argument that links the thermal field double state with ADS CFT. This is the thermal field double Hamiltonian, right? That's the Hamiltonian that's defined on this big factor space. And there are different ways of writing it, right? So in one way, one option is to identify the thermal field double Hamiltonian as just the difference between Hamiltonians of the two copies. And Maldacena and Susskind claim that understanding of the thermal field double Hamiltonian corresponds to this interpretation of the bulk spacetime. A second interpretation they consider is that the bulk spacetime can be interpreted as two entangled black holes and disconnected spacetimes, regions, namely regions 1 and 4, with a common time. And in this case, the claim is the appropriate thermal field double state that's dual to this interpretation of the left-hand side is the time-dependent version of TFD, right? In which we insert a time evolution operator given by this particular expression for the thermal field double Hamiltonian. Right, so that's one version of the second interpretation. The other version is instead of thinking of the two exterior regions as disconnected, we might think of them as connected, right, eventually in the exterior space-time. And so in this case, we have two black holes, two event horizons, right, connected by a wormhole in which the exterior region forms a single connected space-time. Okay, so this second interpretation they refer to as a two-sided black hole. And here's Harlow described in this second interpretation. This is a quote, rather surprising consequence. Two completely non-interacting systems, these two copies of the CFT, can nonetheless have an alternate description where there is a single connected geometry where observers from the right and left can potentially jump through their own event horizons and meet each other in the middle. All right, so that's a summary of Maldaceno's example, right, of interpreted in the second way as two entangled black holes connected by a wormhole. And that's the initial motivation, right, in Maldaceno and Susskind for this hypothesis that in general, two subsystems of a composite system in an entangled state are connected by a wormhole. Of course, it's a big conceptual leap to go from this particular example of two physical systems in an entangled state connected by a wormhole to this more general claim that any two physical systems, etc., right, connected that are entangled or connected by a wormhole. So in the next lecture, I'll look at some additional motivations for the more general claim beyond this first concrete example. Okay, I think that's all I wanted to say at this point.
Does anyone have any questions?
What is equivalence, unitary equivalence of different description? Can you say something more? During the presentation, in different points, there was written that the description are equivalent from a unitarity point of view, so this could be a problem. If you can say something more about this topic.
Oh, okay. Yeah, so the reason I brought that up is, so it first appeared in this first attempt to demonstrate this claim about a vacuum state of a quantum field being entangled in Minkowski spacetime across the left and right wedges, right? And the only point here is that in this way of trying to demonstrate that claim, there's this potential problem of conflating two different representations of the canonical commutation relations, really two different ways of quantizing the field. And it turns out these two different ways, from kind of a technical point of view, at least as I understand it, cannot be equated with each other. Right? And it looks like that's what's going on in write it out in an expression like this. We're equating the vacuum state of a quantum field obtained from one particular quantization method that produces this thing called the Minkowski representation with objects on the right associated with that are produced by another method of quantization, right, associated with this thing called the Fullen representation. And from a technical mathematical point of view, you can't equate. So think of, I think the idea is the Minkowski vacuum is an element of a Hilbert space. The NL in R energy eigenstates are elements of another Hilbert space that's different from the Hilbert space of the Minkowski vacuum. And you can't equate these elements of different Hilbert spaces in this way. I think that's one. I think that's one consequence of this claim of unitary inequivalence. But again, right, it's only a problem perhaps for philosophers who are, and physicists who may be motivated by more rigorous approaches to quantum field theory. Right? For those philosophers and physicists who are enamored of the algebraic formulation of quantum field theory, they like to point out problems with the standard ways of presenting quantum field theory, like these. And the point is, I guess there are 2 points I wanted to make by bringing up this issue. The first point is, even this alternative way of demonstrating entanglement of the vacuum state of a quantum field in terms of path integrals, that seems to be the route of choice of physicists, also seems to face this same conceptual problem, right, at the end of the day. So that's one point. But the other point was just that there are ways of dealing with this problem, right? Even if you're inclined by these more rigorous formulations of quantum field theory, there are general results in these sorts of formulations that allow you to claim unproblematically, rigorously, that the vacuum state of a quantum field is entangled. Actually, there are a lot stronger claims. It's entangled over any arbitrary regions that are space-like separated, not just these two regions of Minkowski spacetime. And the other point is, even if you don't want to go that full-blown algebraic route, right? You can always insert a cutoff into your field theory, and that's another way of mathematically addressing this problem of unitary and equivalent representations.